their damn cell tower.
Oh, Verizon's cell tower fell or something like that. And so they're trying to get it back up.
It fell?
Weird how that happens like 3 times a year.
Yeah.
I don't know what it is. Right now, all I know is that AT&T is ruined.
Yeah.
So AT&T works?
AT&T works right now, which is amazing. It never does.
Okay, so we're going to start in on Chapter 10. So we're skipping Chapter 9. We'll come back and finish that up after Chapter 10. And, you know, the chapters can kind of go in any order, but since Chapter 10 uses a lot of stuff from Chapter 7, and that's kind of what we finished covering recently, I figured it would make more sense to do Chapter 10 now while it's fresh in our head. And it also uses and draws a lot from Chapter 8. And then we can compare and contrast Chapter 9 with Chapter 10. And so it kind of works in either order. And arguably, since the topics are fresher in our head from Chapters 7 and 8, I think 10 actually fits better. So the first thing we want to talk about is intermolecular forces. Intermolecular forces. So this is the attractive force between molecules, or attractive forces between molecules. And so what we've been talking about in Chapter 7 is the bonds between atoms that make up molecules, right? So now we're taking it one step past that. We're saying, okay, we've got our molecule. We know how our molecules are put together. Now we want to know how our molecules interact with each other. And so intermolecular forces are those forces between the molecules. And I should point out a lot of times, well, I use a lot of abbreviations in this section because I don't like writing out the words 50 million times, but intermolecular forces stands for, or IMF stands for intermolecular forces. It also stands for International Monetary Fund, but, you know, we don't worry about that too much because that one's probably one that you're not going to accidentally mistake it for. So there's a series of 1, 2, 3, 4, kind of 5 intermolecular forces that we can talk about. And depending upon what book you read, they'll divide them up differently. According to what book you look at, the last force may or may not be considered technically an intermolecular force since it really is between atoms, but it also is between what we would kind of consider molecules. And so I like to lump it together as an intermolecular force. So the first one we want to talk about are called London dispersion forces. So that stands for LDF. Sometimes they're called van der Waals forces, but we'll refer to them as London dispersion forces, mostly because that's what my other chemistry book calls them, and it's much easier to kind of just have one name for stuff instead of trying to remember which one we're in. So this is the attractive force that exists between all atoms and molecules. And it's technically due to instantaneous dipoles. So as a bit of review, and we're going to talk about this term a lot more, does anyone remember what a dipole is from Chapter 7? It's a separation of charge. And so the idea is that an instantaneous dipole is the dipole that a molecule possesses for a fraction of the time, but that most of the time it's probably nonpolar. The easiest way to think about that is an argon atom. If we take a look at, or any atom for that matter, if we take a look at argon, you know, it's got a bunch of electrons and orbitals around it. And we're not going to be picky about s and p orbitals or anything like that. And so, you know, it's got a number of electrons in its outer shell. And if all of those electrons are arranged symmetrically, let's see, 1, 2, 3, 4, 5, 6, 7, 8. At least I got 8. So there's no dipole. But if at any given instant the electrons on the argon atom are asymmetrically distributed, meaning maybe there's more of them on this side, 3, 4, 5, and at any given moment there's only 3 on that side, then there's what we call a small excess of negative charge and a small excess of positive charge. And so remember that delta means small, and then we're saying that we have either a small excess of negative or positive charge. And remember, for dipoles, opposites attract. And so we know that if I have an argon that has a partial positive on one side and a partial negative on the other due to an asymmetric distribution of electrons, that could be attracted to another argon that has the opposite. So it's got a positive and a negative end like that. And so it's like they're miniature magnets. I almost hesitate to say that because what we should recognize about London dispersion forces is it is very, very weak attractive force. Meaning, compared to the other forces that we're going to talk about in a minute, it's very, very small and almost not worth talking about. I'm trying to remember where in my notes I have the actual value. We don't actually ever calculate values, but sometimes it's nice to have a number to throw at something. And so I was going to see if I could find that real quick, but maybe not. Maybe not. Oh, I do have it as 1 to 10 kilojoules. 10 kilojoules per mole. And that value can vary widely because the strength of that attractive force is proportional to the size or the mass of the atom or molecule. And so the larger a molecule is, the easier it is to polarize. And what that word polarize simply means is the ability to have a small asymmetric distribution of charge. So a small, or to cause a small asymmetric distribution of charge. So it's the weakest force. Essentially, all molecules possess it. But we tend to ignore it if any stronger forces are present. Because they're so much stronger that the London dispersion forces are like a drop of water on top of an ocean. And it's probably not quite that exaggerated. But for most of the small molecules we're looking at, it is. And so really it's only important for nonpolar molecules. So what's a good example of a nonpolar molecule from chapter 7? So nonpolar molecules are usually symmetrical and they don't have large differences in electronegativity between the atoms. So probably the classic example is methane. And what we're saying is that the only attractive force between one methane molecule and another methane molecule is simply this London dispersion force. And so we're showing the intermolecular forces as dotted lines because when we normally drew a solid line, that meant we're sharing electrons, right? So sharing electrons is an intramolecular force, meaning it's inside the molecule and it's between the atoms in the molecule. Intermolecular forces, like the London dispersion forces, are between them. And it's not a exchanging of electrons or even a sharing of electrons. It is just an attraction because of the opposites attract. You can also think about it like the poles of two magnets. And so what we're saying is that even though that molecule is symmetrical, even though we say it's nonpolar, at any given instant there's a small bit of polarity on it. The electrons might be on one side of the atom a little bit more than the other, and so there's a very weak attraction. This is what causes most gases to condense. And the other thing that we can kind of look at is, we said it's proportional to size. Well, methane is a gas at room temperature, right? And as we go up, we've heard of methane, butane, or methane, ethane. We've heard of propane. Propane's a gas at room temperature, right? And that's just 3 carbons with a bunch of hydrogens around it. You guys have heard of butane, right? What state of matter is butane? Yeah, it's kind of a gas liquid, meaning we have butane lighters, right? And so if you put it under just a tiny bit of pressure, it can go from a gas state to a liquid. So it's right on that edge of gas to a liquid. And then if we go up, we can get to eventually octane. That technically has 8 carbons all in a row, and that's gasoline, basically. And we know that that for sure is a liquid. And so notice that as the molecules get bigger and bigger, we go from them being gases because the molecules aren't very attracted to each other compared to the amount of energy that's pushing them around and zinging them around the room. And as the molecule gets big enough and as those attractive forces get a bit stronger and a bit stronger, eventually they condense down into a liquid. And if we go far enough, up to about 18 carbons, maybe 20 carbons, we can actually get those to be room temperature. Or at room temperature, I mean that those would be solids, meaning there's not enough energy to break the intermolecular forces holding them together. So London dispersion forces are weak, but they are important for a variety of things, and we will, consider them in the absence of all other forces that they're there. Okay, the second intermolecular force is called dipole-dipole. And I usually abbreviate that DD because I'm lazy. DD has lots of meanings. It meant double displacement reactions way back in chapter 3. My other class was nice to point out it means designated driver on Thursday nights, which I said, you have class on Fridays, you shouldn't need one. They said, tough. I said, well, that's life. So there's more than one meaning. I can't remember the other one they told me. It was kind of silly. Anyway, what dipole-dipole interactions are is it's the attractive force between the partial charges in an atom, between the partial charges. Remember, that's what we're using this delta plus and delta minus for in dipolar molecules. And remember, from chapter 7, to be a dipolar molecule, that means there's an asymmetric distribution of charge across the molecule. An example of that would be simply an HCl molecule, where hydrogen has a low electronegativity. It's 2.1, so it's partially positive, meaning it's pushing more electrons towards the chlorine. Chlorine has a partial negative charge because its electronegativity, I can never remember, I think it's 3.5. It's either that or like 3.0. But regardless, it's bigger than the electronegativity of hydrogen. And so what we said is that, we can show the distribution of electrons with that partial plus and partial minus, or if we kind of, not hydrogen, but chlorine. If we kind of draw it in terms of the amount of time an electron spends in that bond around hydrogen versus chlorine, then we saw that the electron spends a lot more time around chlorine, so that end is partially negative, and that end is partially positive because it has less of the electron around it than it wants to be. And so the idea is that these molecules then are attracted to each other. The negative end of one HCl molecule is attracted to the partially positive end of another HCl molecule. And then that positive end on one is again attracted to the negative end on another. And so dipole-dipole attractions are simply the attractive forces between those partial charges. I like to think about it as it's also basically the attractive force between the north and south pole of a magnet. So if I have one end be north and the other south, we know that we've got south and north. Now we're covering these real generally. We'll go into a little bit of detail in that your book actually tells you how you can kind of calculate or at least estimate the size of a dipole. Although I have to be honest, we really don't care about it. We don't use it enough for it to be really meaningful, but we might cover it anyway if we have time on sometime next week. Because the attractive force is between partial charges, we give that the term electrostatic attraction. And it really simply means opposites attract. And the strength is proportional to the dipole. And I don't want to cover how we calculate the strength of a dipole because it'll take away from kind of what we're talking about for, things like this, or I guess the big picture, which is all the intermolecular forces, and then we'll go in and we'll look at a little detail of dipole-dipole. Okay, the next one, the third intermolecular force, is called hydrogen bonding. And this is a special case, and we can even say extra strong case of dipole-dipole interactions. So it really has all the same properties of that, meaning it's electrostatic. It really means opposites attract. And the reason it's special for hydrogen bonding, or for hydrogen in this case, is if we take a look at hydrogen, it has only one electron. Therefore, if it shares the electron, that means it has a very large dipole. So if you look at it, here's my hydrogen, and if it's sharing that electron with, say, a fluorine atom, well, that electron is spending a lot more time around fluorine. That means that there's almost no electrons around hydrogen. And that it looks like a bare proton. Meaning it almost looks like a fully plus charge, meaning that partial positive charge is more like a full positive charge. Sometimes I actually just say it's plus plus, meaning it's bigger than average. Now, for that to occur, meaning it has to be hydrogen, so that's kind of the first requirement. Oops, I guess that's technically A if we're going down our bullet point. We'll do it that way. And then the second part is it has to be bonded to a small, highly electronegative element in order to lose the electron to, and I'm going to put that in quotes, we're not really losing it, right? It's not like an ionic bond, but in order to lose the electron to make a large dipole. And small, highly electronegative element really means that the only time it applies is oxygen, nitrogen, and fluorine, meaning these are all in the top row. That means they're the smallest. It also means they have the largest electronegativities. So if we kind of sum those two bullet points up, the idea is that we have to have hydrogen bonded to oxygen, nitrogen, or fluorine forms a extra large dipole-dipole interaction. And actually, one of the things I wanted to go back and see, I meant to put this under dipole-dipole, I apologize. It's one of those little additions to my notes. We said it's stronger than a London dispersion forces. The average value for it is between, oops, that one, where is it? Oh, 3 to 4 kilojoules per mole, which is about 3 times a London dispersion force for small molecules. And then hydrogen bonding, in comparison, when we say it really isn't extra large or extra strong, it's between 10 and 40 kilojoules per mole. So it's about, 3 to 10 times stronger than a dipole-dipole. And if we consider this, and I admit this is well, actually, here, let me show an example first before I get sidetracked. The classic example for this is hydrogen fluoride. And that is going to form an attractive force to another hydrogen fluoride, oops, not hydrogen E, hydrogen fluoride. And that's that partial plus plus and a minus. And so that is my hydrogen bond. One of the pet peeves I have is we call this intermolecular force a hydrogen bond, which makes it sound like a bond, right? But it's not a bond between atoms. It's not even a bond between molecules. It's simply an attraction between them. There's no gaining and losing electrons. There's no really sharing of the electrons. simply is that attraction between plus and minus, or opposites. So technically the aside I kind of want to think about is if we take a graph of boiling point or melting point, it doesn't really matter which one we pick, and then we look at molar mass. So up here at the top we have TE, or H2TE. And I got to be honest, I don't have this graph in front of me, so I don't know the value, but the trend is what's important. And then as we go to a smaller molecule, for instance, H2SE, the boiling point and melting point decreases. So the idea is that there's less London dispersion forces because it's lighter and smaller. And then if we continue that trend, we get H2S. And then what happens is we have a huge anomaly. Water is way up here. And so the explanation for water breaking that is that this is due to hydrogen bonding, not basically London dispersion forces. So the idea is that London dispersion forces, this is where we would predict water to be without dipole-dipole or hydrogen bonds. And so the reason water is liquid at room temperature is because of those hydrogen bonds. If there were no hydrogen bonds, liquid would be a solid at room temperature. And I think life on Earth as we know it wouldn't really work very well. Might happen. I kind of doubt it. Okay, the next one we want to talk about, and this one's, I don't know which order is better to talk about it, but we'll do it this way, is ion dipole. And so this is again electrostatic. It's simply because we know opposites attract. But in this case, it's between a full charge, meaning a full plus and minus or minus, and a partial charge. So ion, if you want to think about it, stands for kind of like in ionic molecules a little bit. So an example of this would be, for instance, if I take, oh, I also should go back. Let us look at one more example for this. I did HF as an example, but really we should point out that water is the classic example of hydrogen bonding because water can actually form two hydrogen bonds. It's actually twice as good as most molecules that simply have an OH, NH, or FH. Oh, we need some waters there. And so for ion dipole, that really explains, for instance, why I say sodium chloride dissolves in water. Sodium has a full plus charge, right? It actually loses an electron. And what that means is that sodium will be surrounded by a shell of water molecules oriented with the oxygen towards that sodium due to the partial negative charges on the oxygens being attracted to that full positive charge on the sodium. We sometimes call this a solvation shell, which is basically the shell of H2O that forms around plus and minus charges due to electrostatic forces. In this case specifically, since we're talking about plus and minus charges, this would be ion dipole. But certainly we can do dipole-dipole, etc. And correspondingly, if I have a chlorine with a minus charge, that's going to be attracted to the partial positive charges on the hydrogens. And so you're going to have a shell of water that's oriented around the chlorine kind of in the opposite direction. Like that. And so this is why ionic compounds dissolve well in water. And we'll actually take a look at this solvation process. I can't remember what chapter it's in anymore. Your book puts things in all sorts of weird places, so I always forget where it is. So ion dipoles are stronger, meaning we're covering this in the order of strength. They're on the order of 10 to 50 kilojoules per mole, depending upon the ion and depending upon what's kind of around it. Oh, look, I have a note. Important for ionic compounds and solutions in Chapter 11. I guarantee you we won't get to Chapter 11 this year. And so for next year, for next semester, which is both, I guess, the same, one of the things we do have to remember and keep in mind is we will be coming back to all these intermolecular forces. They're one of the things that carries over for sure from semester to semester. Let's see. The last one we want to talk about, and this is the one where depending upon the book, you know, they sometimes call this an intermolecular force. They usually call it an intermolecular force, and that's just ionic bonds. And the reason, so this one can be an IMF or it can be considered a bond, meaning an intramolecular force, depending upon the book. I don't think your book lists it, but so when your book says there's 4, what's Jay going to say? There's 5, or at least there's 5. And the reason I like to do it is that it's the logical conclusion or the logical endpoint for electrostatic attractions. And this really is the attractive force between full positive and negative charges, meaning there's no partials anymore. It really is just Na plus being attracted to a chlorine minus, or you know, anything else that has a full positive charge and a full negative charge. And we know that these are the strongest. And in fact, they're so strong that they really are probably what we should consider a bond, not an intermolecular force. But I don't know, I just like to stick it here because to me it really seems to kind of make sense. Okay, so types of questions we can ask are simply something like this. If I have a bunch of molecules, find which ones I selected. Otherwise, I probably just use the ones that are in my book. If I have the following molecules, for example, H2S, CH3OH, C2H6, and argon. What we want to do is we want to list the attractive forces between those molecules. So we've got London dispersion forces, we've got dipole-dipole, we've got hydrogen bonds, we've got ion dipole, and we've got ionic. Notice I've used a bunch of abbreviations in there. I may not have mentioned them, but hydrogen bonding is always HB. Ion dipole is always ID. I think they're fairly obvious what they mean, as long as you've kind of, you know, read the book, kind of paid attention, things like that. And then what we want to do is we want to order them from lowest, say, melting point, boiling point, to highest. And the idea is that melting points and boiling points are essentially proportional to the intermolecular forces. The stronger the attractive forces between any of those atoms, the higher the boiling point is, right? The more energy it takes to pull those molecules apart and go from a solid to a liquid, and then eventually to go from a liquid to a gas. And so the reason that we talk about intermolecular forces is that in Chapter 10, we're talking about properties of solids. And so what determines the properties of solids? Well, a large part of it, especially also in the gas chapter and when we talk about liquids in Chapter 11, is simply these intermolecular forces. So they crop up in every little chapter. So which attractive forces do each have? Well, to really answer that question, we probably should draw a Lewis structure, or at least have an idea of a Lewis structure in the back of our mind, because that way we can see whether they're going to be dipolar molecules or nonpolar molecules, and we can also see when they form hydrogen bonds and when they don't. So I'm going to sketch these here. Now, you know, on a homework or a test, you don't have to sketch them, but you know, 9 times out of 10 an argon is just argon. I usually throw in the word explain in there at some point, and part of an explanation is if you draw the Lewis structure and say, look, it has a hydrogen bond, That's one way to do it. If you simply say it has a hydrogen bond and don't draw the Lewis structure, that's okay too. I just like to draw Lewis structures. They're fun, they're easy, they're good practice. So what an intermolecular force is, oh, I should also point out that since things are proportional to size, a lot of times we want to know their mass. And so notice that one of the things I did is I picked molecules that are all about the same. So, hydrogen sulfide, does it have London dispersion forces? Yes, no. So remember, London dispersion forces is the attractive force between all molecules due to instantaneous charges, or instantaneous dipoles, I should say. So, does it have London dispersion forces? So the part of the definition that said all molecules, right, means that they all have London dispersion forces. That's the gimme question on the test, basically. Then we have to look and say, do they have dipole-dipole forces? Well, remember that in order to have that, that has to have hydrogen bonded to an oxygen, nitrogen, or fluorine. Here the hydrogen is bonded to sulfur, so there's a no. Here we do have some of the hydrogens bonded to oxygen, so those can form dipoles. There's no oxygen, nitrogen, or fluorine in the last two, and argon, doesn't have hydrogen at all. So in this case, only one of them has a dipole-dipole force. And if we look, I'm sorry, I skipped. I should point out, I'm sorry, I flipped which one I was doing, because if I look in my notes, I wrote them backwards. My bad. We're talking about dipole-dipole, so that means we just have to have a partial negative and a partial negative or positive. And so in this case, that has a dipole-dipole interaction also, and so both water and H2S have it. For hydrogen bonding, again, that's hydrogen only bonded to oxygen, nitrogen, or fluorine. And that means that this is the only one that has it, and all the others are no. And then an ion dipole, really, there's no ions in this example, so we really can't talk about it. And certainly the same thing with the ionic attractions. There's no ions present. There's not an Na plus or an Na minus. Argon doesn't form an ion. It's a noble gas. And so there's none of those present. So if I looked at that and ordered it from the lowest to the highest intermolecular force, which one has the lowest there? Well, it's not any of the ones that have dipole-dipole or hydrogen bonding, because those are stronger than London dispersion forces. And so for the first one, I'm really looking at C2H6 and argon. And in this case, C2H6 is probably physically bigger, but argon is physically heavier. And so we said that, it's proportional to size and mass, and since it's really hard to judge size, we'd probably tie break it on mass. And so we could say it's less than or approximately equal to C2H6. And then the next strongest attractive force is dipole-dipole. And so since both of these molecules have dipole-dipole interactions, we have to put one of those next. But note that CH3 also has hydrogen bonding, which is even stronger. And so there's a very clear difference between those molecules and, say, the H2S. Because here we only have LDF. Here we finally have a dipole-dipole. And then kind of much greater than that should be CH3OH, because that has got a hydrogen bond. And so we can tell a lot about these molecules by simply looking at their structures. And this is also one of the reasons why Lewis structures are so very useful, because we are constantly sort of using them to do that. So let's see. We want to also point out, we don't care about those things. Let's talk about dipoles. And specifically, we're going to talk about what a dipole moment is. So this is where I said that, I could put this under our discussion of dipoles, but I wanted to keep it separate from our idea of intermolecular forces. Realize that there might be a question on the homework for this, and then after that, we don't really care because it's such a minor calculation and we don't do it very often, and so we don't worry about it too much. but let's talk about dipole-dipole, or dipole moments. It's given the symbol mu, so that's the Greek letter mu, and we know that mu is equal to Q times R, where Q is the magnitude of the charge. So, and then R is simply the distance between them. Ugh, can't write. Distance between the atoms. And so if you think about it, it makes sense. We know that big magnets equal a stronger attraction. And we know that the distance between, or that we know that the further apart magnets are, so the further apart, the weaker the attraction should be. And so the dipole moment, or the size of that dipole, is simply given by that equation. So the magnitude of a charge is simply a value that you don't have to memorize. It's not on your cheat sheet, but it certainly would be given on a test. It's 1.60 times 10 to the minus 19 coulombs. And this is our unit of charge. And we're not going to worry about it too much because we don't see it again until like chapter 22 next semester. Meaning, you know, we could define what we mean by a unit of charge and a bunch of various other things, but we're not going to worry about the units at all. And then, of course, radius, or the distance between atoms, is generally given in meters. And so a typical bond length, so this is typically in meters and normally on the order of 10 to the minus 12 meters, meaning atoms are really close together. Really close together. And so the standard unit, oops, I guess I'll go back here. The standard unit then for a dipole is something called a Dipole. I'm not even sure I spelled it right. D-E, there's no extra E in there. Dipole. Is that how I always have it in my notes? Yeah, I even spelled it right in my notes. So a Dipole, it's given the capital letter D, and it's equal to 3.336 times 10 to the minus 3 coulomb meters. And so what this means is that for a standard bond, we get an approximate value of about 5 Dipole. And your book, table 10.1, lists some values for common ions, or for common molecules. And so you can kind of take a look at that list and get a little bit of a feel for the size of dipoles. For instance, if we take a look at it, and I think it's kind of worth pointing out, plus I know you guys don't have your books, NaCl, which technically is a plus and a minus charge, has a value of about 9.0 Dipole. And if we take a look at water, which we said is pretty strong, it has on the order of about 1.85 Dipole. And if we go down to something like CO2, which is really pretty nonpolar, we get a value of 0. And so typical values should range somewhere between 0 and 10. And so this is ionic. This has got hydrogen bonds. So what we can use about this then is, because ionic is between full charges, and technically dipoles are partial charges, so partial negative and partial minuses. And you remember back in chapter 6, I think, we talked about that spectrum between ionic, like sodium chloride. Then in the middle we had polar covalent, meaning an unequal sharing. That was like our HF example, or HCl. And then on the other end of our the other end of the spectrum, we had covalent molecules like hydrogen or fluorine where they shared equally. So they shared electrons equally. Here we shared unequally. And here we actually gain or lose electrons. And that's kind of our spectrum. You know, here's black, here's white, and in the middle there's a large chunk of that gray area, which is basically polar covalent. And so what that allows us to do is make an estimate of the percentage of it, or how much of a molecule is, say, ionic. So for example, if I take a look at HCl, we normally think of this as a molecule. But we know it shares the electrons unequally. And so if the idea that covalent would be 0% and ionic is 100%, you know, gain-lose, we can ask basically where in the middle does some molecule like HCl exist? And so if we kind of take a look at it, the theory for HCl predicts that if the dipole moment is 1.82 dBi and the HF bond, HF bond length is 92 picometers, then theoretically the dipole moment should be 1.60 times 10 to the minus 19 coulombs times 9.2, or 92, sorry, 92 times 10 to the minus 12 meters. So notice I converted picometers to meters. And we know that 1 dBi is 3.336 times 10 to the minus, did I really write that out that crappily? Minus 3. My notes say minus 30, but obviously minus 30 is ridiculous. I don't know how an extra 0 got in there. There we go. Coulomb meters. So kind of thinking about it in terms of a bar problem, then theoretically it should be 4.1 dBi, should be the theoretical dipole strength. Now, experimentally, we achieve a value of 1.82 dBi. So the idea is that if I take my experimental value over my theoretical value times 100, then we get that it's about 41% ionic. So the idea is that the dipole is 41% what a real ionic molecule would look like. And so we can kind of say that it's actually more covalent than it is ionic because, you know, it's closer to being 0% than 100%. And we can do this for all sorts of molecules to determine whether things are more covalent or more ionic. Okay, some notes for tomorrow. So we have a test on chapters 7 and 8. Things that you will get on that is obviously a calculator. You get your periodic table. You get your cheat sheet. You get your molecular model kits. And gosh, what's the last one I was trying to think of? Oh, you get appendixes. So you get Appendix B and also miscellaneous tables from the book, which I think the only table really you get is 7.1, which is bond dissociation energy. So you get all those tools. Basically any tool that you would have had available on your homework, you pretty much would get it here. The only thing you can't use in class is you can't Google something and you can't open your book up and try reading around and finding the answer. Test starts at 7:30. test ends at 9:30. Actually, it ends at 9:20 because I forgot I have to be across campus at 9:30. So you've got 2 hours to basically finish the test. Let's see. Anything else? You guys think of any questions? Again, no class on Friday. And we will resume chapter 10 on Monday. So technically on Tuesday of next week, homework 10A should be due because we can finish that up. And then on Tuesday, we'll finish. Oh wait, we did finish that lab, right? Never mind. Lab. Lab 3, I think, on calorimetry is due. And then, Monday we're just going to lecture. And Wednesday we'll lecture. And then Thursday we'll do a lab. And honestly, I don't know what lab we're doing. It's one of them that I need to just kind of find something that fits in. If I actually do the lab I want to do and write it up over Thanksgiving break like I want to do, because I want to be motivated, we'll do that one. And if we don't write something up over break, then we'll just fall back, and there's a couple other labs that we can do that fit into this chapter rather nicely. Now, of course, the coolest lab is if we just had an X-ray spectrometer and we could simply go and determine the actual structure of solids by sticking it in there and doing all the math behind it and stuff. That would probably be the coolest. But since one of those costs several tens of thousands, if not hundreds of thousands, I'm going to guess dollars, not going to happen this year. I keep putting it in the budget, but Todd keeps just saying, Jay, you can't do that. That's bigger than the entire budget, really. And he's right. But I still like to throw